Hey everyone. Oh, mic works, which is great. All right, I think we'll plan to get started. So welcome to the session on behind the scenes for Azure Block Storage, unique capabilities. I'm Yuming, Principal Product Manager from Microsoft. I'm very excited to be here. Reason is that I eventually got to talk about something I worked for 9 years when I started my career working on the first storage client driver that is supporting the SSD-based block storage premium disks. And I'm here co-presenting with Greg. I'll let Greg do his intro.
Hello, everyone. I'm Greg Kramer. I'm a software architect in Azure Storage. I'm actually here today filling in for a colleague that couldn't be here today. Malcolm Smith, he works on a related team in Azure Storage, so pardon me, I'm going to do my best to represent him and his team, but I may have to defer some questions till later.
All right, let's get started. So we'll do a quick kind of walkthrough of what is Azure Storage, and then we'll jump directly into the unique capabilities we offered, but more as how we are able to build it on top of our XStore stack. We'll for sure leave some time at the end for Q&A. All right, so for Azure Storage, we offer a comprehensive portfolio of all the storage offerings. We have Disks, which is the block storage offering. Going forward, I'll just use this to refer to Azure Block Storage. And then we have Azure Blobs, which is the object storage, and Azure Data Lake Generation 2, which is built on top of Blobs and provides HDFS support. Lastly, we have the file storage and also hybrid storage solutions. So if I actually look at all the storage offerings we have and then overlay it on top of our stack, you could see that we have like blocks, Azure Blob files, and also part of the Azure Block Storage standing on a single storage architecture, which is, we call it XStore. And on top of this architecture, we actually provide optimizations per each specific services so that you have different performance and price point and interfaces for the targeted workloads. And then for the block storage, we also have it on a new stack, which is what Greg delivered the previous talk about direct drive. So as this talk is specifically on block storage, we'll just zoom in and take a look of our block storage portfolio. So going from the right to the left, you could see that the performance and the scale goes up. So for standard HDD, standard SSD, and premium SSDs, those are hosted on our XStore stack, where the premium SSD version 2 and then UltraDisk is on the direct drive stack, which is the newest, latest stack that is optimized for performance. Specifically on today's talk, we're going to talk more about XStore. Reason is that we have evolved the XStore stack for past years and added a lot of comprehensive capabilities on the XStore stack that is best fitted for lift and shift workloads and all that. So I will do a quick kind of high-level overview of the XStore stack. So for XStore, it is a 3-tier stack. 3 layers, starting from the top, which is our front-end layer. This is where it's, the front end actually process all the incoming traffic. It provides the protocol endpoints, authentication, authorization, and then the logging and metrics. Then we have the middle tier, which is the partition layer. This is where you can see that this is the layer that understands the business logics and then manages all the data abstractions. That's where it presented the data as in blobs, files, and block storage that you see at the different services. You can consider this as a massive scalable index, which actually are able to kind of map each of the objects to the specific streams and the data stored in stream layer. The last layer is on the stream layer. This is where it actually writes the bits into the actual hardware. And this is where it manages the replication and also the distribution of the data across servers within a cluster. It sits on a JBOD, and then it's an append-only file system. So in the later talk, we're going to talk about one of the specific replication or redundancy option we offer, which is called Zonal redundancy storage, and we'll come back to the stream layer a bit. So, for XStore, there is actually a paper on this, so you can find it online. We also did a a talk in STEAM, I think, a couple years ago specifically on this. So there are a lot of materials online about XStore if you're interested to know more. So for today, we are going to talk about specific unique capabilities that we support on XStore. We picked 3, which we think are very representative that only Azure offers compared to any other cloud providers. The first one is regarding of instant snapshot and restore. So this is critical for any enterprise workloads which they are using block storage. They will want perfect, the best RTO and RPO they can offer on any cloud. Second is that we'll talk about the data access over different protocol path. So we have the single XStore stack where you could actually have both SCSI and also REST, different path for you to do data access on your storage. Lastly, we'll talk about the highly scalable, highly available storage, which is our zonal redundancy storage, which is synchronously replicated across 3 availability zones in Azure environment. I'll put a disclaimer first, as we will be talking about the capabilities and also the engineering design. So specifically on how these capabilities applies or offered on specific SKUs, we recommend you to refer to our product page for that. All right, so let's talk about instant snapshot, create and restore. So what is a snapshot? So basically, snapshot is a point-in-time capture of the state of your disk. We support so-called incremental snapshots, as we only capture the changes between your snapshots and changes on your disks on the snapshot. So you'll be saying that, oh, it's just a snapshot, kind of doing a versioning. What's so fancy about it? What is unique is that we are able to provide snapshots in the choice of your storage. Meaning that if, let's say, your disk is hosted on SSD, you will be able to create a snapshot either on SSD or HDD and be made instantaneously available. Similarly, on the restore path, you could have your snapshots in HDD, which you store it for cost savings, cheapest storage you can buy. And then when you're trying to restore, you'll be able to quickly create a disk in a higher performance tier, which is referencing using the snapshot in a lower tier storage. Also made it instantaneously available. So how do we orchestrate this flow? Let's say the large cylinder on the right, that represents your disks. And then you have the pages written in this disks, which is colored in green. So, we use a coloring just to show that you can write different page ranges, but we are a append-only system, so it's not really that you actually kind of located in different, you have kind of gaps in between, but just an indicator as the page ranges you have written. So what we do first is that we create something called a reference blob. What this reference blob has is that it has a shallow copy of the disks where we capture what is the pages and indexing for the pages you have written, and also the properties of the disks. So in this reference page, when it's getting reference blob, when it gets created, it basically have a standalone life cycle of the disks. At this point, if you go and delete the disk, it's perfectly fine. The reference blob has all the information that is needed to construct a snapshot. Our next step is to create a copy on the target cluster. So going back to the storage of your choice, your target cluster can be completely different than your source cluster. It can be hosted on HDD versus your source cluster is all on SSDs. So in this case, we create something as a copy blob. What is unique about this copy blob is that we have a technology called copy on read. The moment you create this copy blob, we will be fetching, doing a background copy of the data from the source into this copy blob. Similarly, if you have new reads that is made to this copy blob, and if the data has not yet been replicated from the source, we will go back to the source and actually fetch the data, persist it in this copy, and then return it to the user. So in this case, the copy blobs on the target cluster is basically the snapshots that we actually funded to the user, where the reference blob is something which is the internal implementation, and that will be hidden on the user end. When the copy is completed, at that point, we're good to delete the reference blob. You no longer need it. So our snapshot is also incremental. So what that means is that you could have, let's say you wrote the read the green areas, and then you create a snapshot. Then you make some changes regarding of your disk, and then write the yellow part, which are your changes. The flow is very similar, where you go and create a reference blob, and then from a reference blob, you will go and create a copy on the target cluster, where Azure will dynamically do the identify the changes of the latest snapshot versus your previous snapshot that is made available in the target cluster. So in this case, if you have the green snapshot, which is already available, the new snapshot will only capture the changes, which is the yellow piece. But let's say you don't have a previous snapshot. In that case, the new snapshot will capture both the green and yellow area. So we just talked about create, where we'll talk about the restore part as well. So when we say snapshot restore, this is where you're able to create a disk from a snapshot. So the restore flow is slightly more complicated. As you can see that the moment the disk is created, you need to handle both read and also write traffic from the user. In this case, the green, kind of cylinder is the snapshot you have created. Same first step, you'll go and create a reference blob. Same idea. This is where you have a shallow copy. The moment the reference blob is being created, you can go ahead and delete your snapshot, and that will not impact the life cycle of reconstructing the disk. Your next step is to create a copy blob on the target cluster. So your target cluster can be HDD or SSD based, regardless of where your snapshot is being stored. So in this case, if you're using HDD for cheap snapshot copy, you can still immediately actually create a high performance disk out from that snapshot. So as the snapshot is getting restored, we also create something we call a differencing blob, which is there to actually handle the new coming write. So both the copy blob plus the differencing blob together composes the new disk. From a user perspective, they will only see a single top-level resource, which is the disk. But in the background, we actually have these two blobs, which is hosting the data for this one disk. And the copy blob and the differencing blob are there for the entire lifetime of the disk. So here you may have a question as, okay, so when you have a differencing blob, you'll be writing data into that differencing blob, and then it will overwrite the pieces of ranges which you have copied over. So you'll have some inefficiency here where, same range, you can have an old copy and then a new copy. So we handle this as the moment when you have the page ranges which is overwritten, we will actually mark the original page ranges, and then we have our existing garbage collection process to actually reclaim that resource. So we are, going back to XStore, we are a append-only system. So this is something which we do it not only for this scenarios, for all the scenarios when you have an append-only system. That's where you'll be marking, the overwritten kind of the page ranges or the data sectors, and then leveraging a garbage collection process to kind of free up those resources. So in this case, I think if you look at it, we kind of walk through regarding of the snapshot restore flow. So I wanted to kind of just quickly go through the data path so you have a better understanding of how we are actually, serving the read and write traffic on this newly restored disk. So let's say if you have a read which hits the new disk, what it will do is that it will first actually hit the differencing blob. So you'll try to figure out whether it's in the differencing blob as that being recently written. If it's not available in the differencing blob, we'll go and hit the copy blob. So if the data is not yet being background copied from the source to the copy, we will go back to fetch the data from your source. So that's for read. Write is much simpler. Write will always go to the differencing blob. Same idea, copy blob and also the differencing blob will live for the entire life cycle for the disk, where when a copy is being completed, you can go ahead and delete the reference blob. As you can see that the way Azure, we are able to support the instant snapshot restore and create, it's all, leveraging the copy on read technology that we have, where in the copy blob, we have the orchestration of reading the data from the source and also being able to fetch the data on the fly if they are incoming reads, which are not already being persisted in this copy blob. What are the other use cases for core? So copy on read, we just call it on core going forward. The other use case we leverage call is for provisioning VMs from a single, golden image. So let's say you kind of have baked a new kind of Linux distro, and then you wanted to do a scale testing from that. What you are most likely going to do is that you have a single golden image, and then you will create multiple VMs from that single image. In this case, all the VMs will be using the same, golden image for bootstrapping. And then all the VMs will also need its unique disks for capturing the differences, which are the latest changes. You would also want the scale of this new VMs to be very fast, because if, let's say, you're scaling up your VMs for a production workload to handle additional traffic, you don't want it to be there waiting for your VMs to come up. As you can see, this will easily impose a challenge where all the VMs started to read from the same golden image, where the performance of that image will be limiting on the factors of how your VMs and your disk performs. The way we handle this problem is by constructing a copy on read tree. So on the top, you can see that is the image. And then we will go and spin up new source cores that are pointing back to this image. So the moment the source core is getting created, it will be reading the data from the image and then populating the source core. Then you have child disks, which is pointing back to the source core. So each of the child disks will have their own core and also a differencing blob, just like the disk restore scenario we just talked about. In this case, you can see that, let's say you have a VM that disks, you're trying to read from that disk. That disk will, the read to that disk will first go and attempt to find the data in the child core, then going back to the source core and then back to the image. The reason why we structure it this way is that you can see the middle layer regarding of the source core is basically copies of the images where you could create them instantaneously, and then in the background, pulling the data from the image so that you're not having all the childs going back to the source image and then create a bottleneck there. We could scale out these source cores as basically adding more of the source cores, or kind of scale it in a vertical manner. Depends on what is the scale that we are talking about in the VM provisioning scenario. All right, as you can see, for constructing a core tree for the VM provisioning scenario, we need to also tightly manage the lifetime of the source core. Because when the child has all the data written, all the data, replicated, you don't want it to keep the source core forever, because that will add additional costs for your system. There's inefficiency there. So we need to manage the lifetime of the source core. To do so, classic kind of a referencing counting issue, which is that you need a reference on the source to actually track the dependent children. So in that example, each of the source core have like 6 children. So in this case, we need some manners to actually know that, what are all the children that has dependency on the source core. So you can't go ahead and delete the source core if they're still dependent children. This is quite challenging, as if we can't really do a simple reference counting with numerical values, because it's very hard for you to guarantee that the add reference operations is applied exactly once. So think about this in the distributed system, where you could have packet loss, and then your child will go and retry, trying to do this add reference, and then easily lead to incorrect reference count on the source core. The way we address this is that we kind of look at what is our design principle to kind of managing the lifecycle for the source core. First thing we wanted to guarantee is that a child should only have a single reference on the source core. Then, to achieve that, we are implementing an add reference call, which transactionally record the identity of the child. The identity of the child includes the UI of the child and also authentication information for the source to actually make calls against the child. We ensure that the at reference call is idempotent, so that in each of the source, you will only have one record for that unique child. The diagram showing here is just an example. As on the source, you have 6 children, and then you'll have kind of a list of all the identities of the children that has dependency on the source core. Still, this is not perfect, because how do I ensure that a child would only have a single reference? Because in the creation of the child, you'll need to solve the problem as whether you wanted to create a child object first or take the reference first. So it's hard to guarantee that both will happen simultaneously. So the decision we have taken is that we will always first take the reference. So what it means is that whenever you're creating a child, which is spinning off from the source core, we'll go ahead and first take the reference on the source, then create the child object. That means that you'll potentially have, leaked reference, as when you take the reference and then attempt to create the child object may, failed, or there are reasons that it's just kind of deleted, or the call itself, we just don't want it to proceed forward. So you could have, leaked references in this case. We approach this problem to do the reference management from 2 sides. One is that on the source aspects, what we do is that whenever the source core get a call from any of the child on a delete reference, or it receives a delete for its core itself from an upper level resource manager, the source will explicitly call a break reference across all the children's. So no matter whether you have, kind of called the delete reference or not, we'll attempt to break reference. And if the break reference call actually failed due to the reference not found by using the identities that is stored on this child, we will treat this as a leaked reference. What we'll do is that we'll go and delete the reference. We also look at it from the child aspects, where whenever you're trying to delete the child, you'll first go and delete the reference on the source. So we have a process in place to retry on the delete reference to ensure that it eventually will succeed. And this is what we do in the way of deleting a child. So you can see that the delete reference is a sole responsibility on the child side. So it's quite a journey where we started first talking about the instant snapshot, restore, and creation, that's where we introduced our copy on read technology. Then we talked about how we are using our copy on read technology for doing VM provisioning. And then we shared about, in this way of using the core as constructing a core tree, how do we handle specific challenges in doing the reference counting. So I'll wrap this part up, and then I'll turn it to Greg to talk about our next unique capability, which is supporting data access over different protocol paths.
So one of the interesting capabilities of the XStore architecture is the ability to support access to your block data, not just through traditional block protocols like SCSI, but also through additional protocols. I'm going to talk about that a little bit. You can get SCSI out of the way quickly here. Obviously, the traditional way to access your disk data is going to be to attach that disk to a VM running in the cloud. SCSI is probably one of the older and most mature protocols for giving access to that data, and so of course we support that. In the last talk that I gave, someone asked about NVMe, and the answer I gave there was that we don't have anything specific to announce, but in choosing which block protocol we were going to go after first, SCSI was sort of the obvious choice because it is the most widely supported. I mean, one of the things that we see is that customers, bring their solutions from on-prem into the cloud, and oftentimes these can be based on quite old operating systems that may not actually speak NVMe yet. So SCSI was sort of the obvious choice here to start with. The interesting use case, though, here is the use of REST. And so the XStore architecture allows you to access your block data through HTTP REST requests. Now we can go through an example of why that might be interesting. So if you consider a sort of standard disaster recovery solution, you might want to replicate your data from one region to a completely different region, so in case it gets taken out, you still have access to your data. And the standard way of doing this would be to stand up another VM in the secondary region and then use some sort of technology to replicate your data. So Windows Server, for example, has block replication built in, or rsync, or there's a zillion ways that you might do this. The downside of this approach, though, is that you actually have to run a second VM. VMs cost you money, right? And so sitting there with that other VM replicating the data into your second region, it's just costing you the entire time it's up and running. What you'd really like to do is to be able to move that data to your secondary region without having to run the VM. Now, had we only had block storage protocols like SCSI, that would have been your only choice. But with REST, you can move that data to your secondary region without having to run the VM. So we can take a quick look at what that might look like. In your primary region, you can take snapshots, which Yumin has already spoken about, and the snapshots support incremental data transfer. So these snapshots exist as objects that are accessible through the blob store using REST APIs, which means that you can write software using REST that's capable of taking those snapshots, copying them to your secondary region, and then as new snapshots are created in the primary, you just pull the diff using the existing REST APIs and then apply those diffs in the secondary location. The way that the REST paths is implemented is in the FE, or front-end layer. So the FEs are sort of like gateways to the storage service in XStore, and the FE is broken up into two layers. So the protocol layer is where we can introduce new APIs, new ways of accessing the data. So this would be where our existing network requests come in from these SCSI initiators, but also our REST APIs are implemented here. Underneath that layer in the FEs is what they call the service layer. The service layer is where we have our internal primitives that allow the XStore storage stamp to get and retrieve data. And so the core idea of the FE is that we can introduce new APIs fairly easily in the protocol layer without anything underneath it needing to be affected or aware of that, because it's all using a common internal interface from there on out. The next thing that we'll talk about is ZRS. So in Azure, we have a replication strategy referred to as LRS. This would be 3 copies of your data that's created inside a single data center. Now, data centers are fairly survivable entities, but disasters happen. They are powered by regional power sources. And for certain workloads, you want to make sure that a disaster that would take out a data center would not prevent you from accessing your data. So different zones are physically separate areas within an Azure region that are fed by independent power sources or have independent cooling and are meant to stand alone, so that if one zone goes down, the others are very likely to survive. ZRS replication allows you to create a disk, perform I/O to it, and have the XStore system replicate that data for you across those zones. So this is showing an example of an HA setup that you might create using ZRS replication. So you've created a ZRS disk here, and you have a VM that's doing I/O to it, the primary VM in zone 1. The XStore layer is handling replicating that data synchronously, such that if zone 1 were to die, you could take one of your secondaries, spin it up, attach to the disk, and immediately pick up where you left off before. Now, this is a unique capability to Azure to replicate your data synchronously like this underneath the covers across 3 zones. The way that ZRS is implemented is that as writes are performed to the ZRS disk, those writes flow through the FE to the partition layer, the table server, where they're passed off to the stream layer, the ENs. The ENs then handle replicating that data to the other zones. Reads are issued, or could be issued, to any FE. In this example, we show that the reads are going to an FE in zone 2 that passes it through to the table server and the EN succeeding the read. But if zone 2 were to go down, those reads could be forwarded to an FE in either zone 1 or zone 3, and you would have immediate access to the data as it was last written.
I think we can, we wrapped up our talk, and then if you have any questions, feel free to raise your hand and speak up. All right. Very good question. So let me pull it back to here. So I think, okay.
Repeat the question.
Oh, sorry. Let me repeat the question. So the question is regarding of how does XStore related to direct drive, and if that's the backend implementation. So I think going back to this, XStore and direct drive are two independent stack, where direct drive is where we are supporting on the premium, the newer disk offerings, and then we have XStore supporting the standard HDD to the premium SSDs. So they are standalone, but then we also provide data movements for customers for us to move data between these two stacks. So they are not in the isolated stack, but they are kind of two separate. Does that address your question? Okay. Oh, so the question is that does both SAP provide SCSI access from Hyper-V? Is that? Mm-hmm. Yeah. No, so if the question is specific, so the question is that can these disks be accessed through iSCSI? So today, for for disks, no matter it's on the XStore or the direct drive stack, from the guest to VM side, it can only be accessed through SCSI. It doesn't support iSCSI. But if you go back to kind of what Greg talked about, our ability to add different protocols on our single XStore stack, in the future, we could add, more protocols, but there's nothing that we support iSCSI today. All right. So the question is that for the ZRS disk, when do we actually acknowledge the write back to the client? So the way that I think we talked about is that for the ZRS disk, the write to these three zones are synchronously being written across the three zones. So the idea is that for the specific zones that you hit, let's say it was zone 2, that's what we have the example, where on the stream layer, it will replicate the data to the zone 1 and zone 3. Only until zone 1 and zone 3 completed the write, and also the within zone 2 write has completed, we'll go back and acknowledge the write has been completed. Very specific product question. So I think if my memory is right, today we support 200 snapshots per disk. And these snapshots, just to kind of drill a bit deeper into this, all the snapshots we provide today on disks, they are standalone, meaning that they have an independent lifetime of the disk itself. And for snapshots, you could create whether it's full snapshot or incremental snapshot, but roughly I think it's 200 per disk. I'll go with that first. Yeah, that gentleman. Do you mind repeating? Oh, so your question is that how do we handle the zonal replication if a zone goes down? Did I understand it correctly? Okay. So I think that this is where on the ZRS cases that when we actually, our intent is to actually replicate across the 3 zones. But if one zone actually goes down, we have an implicit logic that we will be, replicating against the 2 available zones. And then the other zones, when it comes back, so we will try to, reattempt on the replication. Good question. So what your question is about, how do we switch between the disk between XStore and direct drive? So today, we actually, from a user experience perspective, we don't support that. But the way which we are looking to support it is kind of leveraging the snapshot, where you could use snapshot as to create a point in time, then create a new disks on whichever the stack you decided to go with based on the disk you choose, and then use that to actually do the, do the restore. Very much like the copy on read that we just talked about. So I think the question is that for the XStore and then the direct drive stack, what are the key differences? And then whether it's just on the performance or there's anything else that we wanted to, different considerations that we have on this 2 stack. So right now, I think if you go back, so for the XStore stack, it is a 3-layer architecture where the direct drive stack, I think Greg talked about, so it kind of removed the layer for both on the front end and also the partition layer, so that it's very much optimized for block level access. So from a performance perspective, direct drive will definitely provide better performance at its optimized for that. I'll let Greg also comment on this in a bit. And then on the XStore, as you can see, for XStore, we have these layers. The layers are there for a reason. For example, they're there to actually provide the additional protocol support on that. So if you look at how we position these 2 stacks, the XStore stacks is that we have comprehensive capabilities which are optimized for lift and shift, because a lot of those you need, SCSI protocol. Actually, on the same stack, we support our blob and file storage, which you have SMB and then NFS and all that. Where on the direct drive, it's purposely built for highest performance block storage. Anything, Greg?
Yeah, the other difference that I would call out is that direct drive allows you to independently provision IOPS, bandwidth, and disk capacity. So instead of buying performance in fixed size units, you're free to choose the disk size that you need and then select however many IOPS or how much bandwidth you need based on that.
Yeah, go ahead. The question is that does direct drive support snapshot and copy on read? Right.
So architecturally, the answer is yes. I'll say what I said in my earlier presentation, which is for any particular product you're interested in, I would direct you to the product pages.
Oh, go ahead. The performance differences, I think, let me try to see if I can address this on the offering perspective to give you a bit of sense. So it's very hard to directly just say from a stack perspective. We can talk about the product that we offer. So let's say we take the premium, but I do wanted to put a disclaimer. What you get on the product is not exactly what the stack is able to offer, but I do wanted to provide some data points so you have some idea. So on the premium SSDs, which is on the XStore stack, roughly from performance perspective, it can scale to roughly double-digit thousand IOPS in that range. And then the latency is more around the 1 millisecond ranges. Where on the direct drive on our Ultra disks, those ones can easily scale to more than 100,000. And that's not, that's not the max we can do. The stack can actually do better, but right now on the product offering, that's where it is. And then from a latency perspective, it's definitely in a consistent sub-millisecond range.
Big data type workload, then usually cloud guys have this locally attached storage. Is that, so for example, you will have a node that will have 64 terabyte of locally attached PCI storage with NVMe. Do you serve those use cases with Ultra, with direct storage, or you have a separate service for that?
Okay, so the question is that for most of the virtual machines or instance, some of the ones you purchase on cloud, you have local attached storage. Usually, I think each cloud provider stated differently, like temp storage, local SSDs, and all that. Do we serve it by direct drive stack? So today, no. So today, all the local SSD or temp drives that you get it on the virtual machines on Azure, those are locally attached. They are not sitting on the persistent storage stack. So today, for both XStore and direct drive, those are all persistent. We have different redundancy options, but in compared to the local SSDs you're talking about, those are kind of with the lifetime of the VM, and those are not persistent storage. But they are still serve a very good purpose that sometimes if you just do kind of large data analytics workload or you just need local caching, those are perfectly fine. You don't really need it to be persistent, and it is locally attached. Yeah, go ahead. So the question is that do we support any data reduction capabilities or compression? So no, we don't. From a user perspective, we do not support any data reduction or compressions, which is user facing. As when you buy a disk on Azure and say you have data reduction and compression, no, we don't support that. Do we plan to? I think that is a very good question. I think we hear very mixed feedback from users on whether they want this. I think definitely in the end, they don't want it because they wanted to do data reduction. They want it because they wanted to eventually, reduce the cost they need to pay for the disks. So I think it's just different way to kind of skin the cat. As in the end, if you have a TCO which hits their needs, whether you take approach to directly expose, data reduction or compression versus you actually just give a price which is lower on provision wise, it'll serve the same purpose. So right now we don't have any plan disclosed in sharing in doing kind of customer facing compression or dedupe or reduction. Yeah. So for back. So I think. So definitely on the storage stack, we do optimization so that we can reduce the overall costs. I can't speak more on what we do, but the idea is that we will, the approach which we have taken is that we will be doing optimization so that from a user perspective, you get the lowest dollar you need to pay for this. Yeah.
You mentioned on slide 24 that you're supporting SCSI and REST, and it says other standard block storage protocols. Any comments?
So I think on this one, what we are attempting to kind of deliver the message is that with our tier stack on the FE layer, today we have REST supported there. We could easily add a new protocols besides REST. Right now we don't have any, but this provides, the stack itself provides the opportunity for us to add any other standard industry protocols. Good question. So I think for Azure, we by default support something called server-side encryption with platform managed key, which Microsoft basically have the key to encrypt all the data. So if you don't do anything, it's always encrypted by Microsoft managed key. So encryption is there. We also expose the capability of encryption with customer managed key. So in that case, you are able to actually have kind of upload your key into something we call it a key vault, and then use that key in the key vault to do the encryption for the disk. Yeah.
For the Microsoft encryption, is it at the front-end server, or where in the stack?
So the question is that where in the stack that we actually perform the encryption. Greg, do you want?
So the XStore classic stack, encryption is done by the front end. Direct drive,
So I think Aaron, Aaron is our helper on the audience seat. Aaron's answer was that on the XStore stack, the encryption is done on the FE layer, and then we'll let Greg comment on the direct drive.
Right, so for direct drive, architecturally, we support encryption happening either at the disk client or in the CCS for the write path. So it's just a configuration option.
As a comment in general, no data at rest in Azure is unencrypted.
Yes, that's true. Yes, the comment there was that the general guarantee we're making is that before any customer data is committed to a durable media, it is guaranteed to be encrypted.
Right. Any questions? Not. Oh, one more question. So the question is that what about data in flight? Did we touch about the different protocols? So I think for both XStore and direct drive, from the client, which is the compute where your VM sits, to the storage, we all use a proprietary protocols on that. Specifically on direct drive, I think Greg talked about in the previous talk. I'll not repeat that. Similarly, on the XStore, we have our proprietary kind of protocol, which talk from the client to the backend. Specifically on this area, it is actually going through kind of the network backbone, which it is strictly kind of managed by Azure from the compute and storage. So we don't have anything. It's not like in the sense that you have, SMB, and then SMB does the specific network additional layer of the encryption on that protocol itself. So we kind of are leveraging our network infrastructure to ensure that the security from the compute to the backend storage communication. Sorry, I got the last piece. Just let me rephrase and make sure I understand it correctly. You are stating that for the storage stack, we have Hyper-Vs and then our storage client drivers. Your question is that is it in the same box? I'm not sure I get. Okay, the question is that is storage a separate server? So our storage are in a different cluster than the compute. So basically, the storage servers are on a on storage clusters where your virtual machines are in the so-called, we call it compute clusters. So they are remotely attached. I think we are. I don't know if we are running out of time or I think it's. We are at time. All right. One more question. Yeah.
Well, two actually. One,
No.
administrative, I saw some differences between the presentation you showed and what is currently uploaded. Will you be uploading the version?
Yes. Yes. I think we uploaded a new version. Probably it's not yet being synced yet. I think we'll make sure the latest version is getting uploaded.
And I wanted to point out, speaking of encryption, you may want to look at the new IEEE standard 2883 about sanitizing storage.
So this is a recommendation for us to look at the new IEEE kind of encryption. Yeah, we'll take a look. Yeah. I see. Okay.
For those of you here, we'll have a full section on that.
Oh, that's great. Then I'll go to that session. All right. I think we're good. And then I think Greg and I will stay around for a bit in case you have any other questions.
Thank you.
Thank you.